Hi there. In this video, we're going to look at how to find the derivative of an inverse function, and we're going to talk about a very important quantity called the Jacobian and how the Jacobian is used to find the derivative of an inverse function. So we could have some function u, for example, which is a multivariable function that depends on x and y. So we could say that u is equal to e to the power x multiplied by cos y. We could also have another function v. V is equal to e to the power minus x times sine of y. So thus far, you've seen that it's quite a simple matter if we wanted to determine day u, day x. Well, this is just equal to, keeping y constant, this is just cos y, the constant, times the derivative of e to the power x, which is just e to the power x. So it's quite a simple matter to determine day u, day x. So the question that we now want to answer is it possible to find the derivative of the inverse function? That is, instead of day u, day x, can we determine day x, day u? How would that even work? Well, the first inclination would be maybe to think about something along the lines of, can we somehow represent this equation in terms of x and put it in terms of u, make it somehow swap the variables around, do some algebra or something like that and try and manipulate it and then find day x, day u? It might be an option in different cases, but often it might not even work out. We would just end up with an implicit function. So there is a way to do this using the differential function or the function differential that we have been considering in the previous videos. But in any case, if we're determining day x, day u, we could also determine day x, day v, and also day y, day u, and day y, day v. So we will start off with the function differential as we've been expressing it thus far. We would say delta u is equal to day u, day x multiplied by delta x plus day u, day y times delta y. And we would do the same with v as well. We would say delta v is equal to day v, day x multiplied by delta x plus delta v or day v, day y times delta y. So we're now going to be performing some mathematical manipulations here. The first thing that we're going to be doing, well, before that, let's call this equation 1 and this equation 2. So what we're going to do is we're going to take equation 1 and multiply it by day v, day y, and we're going to take equation 2 and multiply it by day u, day y. So let's do that. Equation 1, we're going to multiply this by day v, day y, and equation 2, we're going to multiply this by day u, day y. So if we do that, we're going to end up with, let's just take this down. So it would be day v, day y times delta u equal to day v, day y times day u, day x, delta x plus day v, day y times du dy times delta y. And of course, we do this now with equation 2. So we're multiplying dv by du dy. Du dy multiplied by delta v, and that's going to equal to du dy times dv dx times delta x plus du dy times dv dy times delta y. So the next thing we're going to do is subtract these equations. So let's call this equation 3 and equation 4. So we're going to take equation 3 and subtract it from equation 4. So when we do this, we get dv dy times delta u minus du dy times delta v. And this is equal to, we can take out delta x as a common factor in both these equations when we subtract it. And of course, we see that these terms cancel out. We have dv dy, we have dv dy, we have du dy, we have du dy, and delta y. So both of these will cancel. And what we're left with is these two terms and delta x as the common factor. So that's what we're going to write on the right-hand side. We have du dx multiplied by dv dy minus dv dx, this, and what's left is du dy. And of course, multiplied by delta x. So if we now solve for delta x, we make delta x the subject of the formula, as they call it. We get that delta x is equal to, well, everything that's on the left-hand side at the moment. That's dv dy times delta u minus du dy times delta v. Sorry, that should be a v. Then all this is divided by well, the term that's on the right-hand side. That will be du dx, then dv dy minus dv dx times du dy. Okay, so we can repeat the same thing for y. That is, instead of making delta x the subject of the formula, we make delta y the subject of the formula. So how we would do that is, instead of here we have equation 1 and equation 2, so we would swap these things around. We would multiply it by, instead of day v day y, we would multiply it by day v day x, and we would multiply it by day u day x. We multiply equation 1 and 2 by those two things, and then we repeat the exact same process. And all of this would be to now express this in terms of y, delta y. So in equation 3 and 4, when we subtract it, instead of the delta y's cancelling off, what will cancel off is the delta x. So it's a simple matter to do this, and I expect you'd be able to do this part. But when we do that, we find that delta y is equal to day u day x times delta v minus day v day x times delta u divided by day u day x times day v day y minus day v day x times day u day y. So looking at these two results, we see that the denominators are the same, right? So look at when we made delta x the subject of the formula. Look at the denominator. We have day u day x, we have day v day y, we have day v day x, and day u day y. Now looking at the denominator when we made y the subject of the formula, we have day u day x, day v day y, day v day x, and day u day y. So these two denominators are the same. So this denominator we can see is actually of a specific form. It's actually a determinant. So if we were to write the determinant of the denominator, we have day u day x, we have day v day y, and then we have day v day x, and completing it is day u day y. We can see that this is the determinant. Day u day x times day v day y, this is the first term, minus day v day x times day u day y, which is what the second term is. So we see that the second term is actually a determinant, and that determinant is given the name the Jacobian. Or the letter J. You just call it J. J for Jacobian. So if we carry on with our exercise and we're looking at delta x and delta y, well, we have it already in terms of delta x and delta y. And what do we want to determine? We want to determine day x, day u. Sorry, this does not look like a u. We want to determine day x, day u, and day y, day u. So what do we need to do? Well, we take this delta x and we divide it by delta u. That's all that we're going to do. So if we divide this by delta u, we're going to divide this entire thing by delta u. So dividing the terms in the numerator by delta u divided by delta u is going to cancel off. So that it doesn't cancel off, it becomes 1. And delta v, well, if we're going to find the derivative with respect to u, it means we're keeping v constant. So this term is a constant, literally, and that means that it's going to become 0. So all that we're going to be left with is day v day y divided by the Jacobian. So let's call this equation 5 and equation 6. So the next step in this process is to take equation 5 and divide it by delta u, and then take equation 6 divided by delta v. Actually, we can divide both by delta u and delta v because we want it in terms of x and y. Okay, so it's divided by delta u and delta v. Okay, my cursor seems to have disappeared for some odd reason. Okay, we're dividing it by delta v and delta u. Fantastic, my cursor has appeared again. Wonderful. So once we do that, we then let both of these things approach 0. And following on from that, we're now able to find day x day u and day y day u. So this becomes divided by delta u and also delta v. We do it both ways. And when this approaches 0, this becomes day x day u and day y day u. And of course, this becomes 0 and this becomes 0 as well. Sorry, we can divide this by delta v. It depends on the variable that we're holding constant and dividing by at that moment in time. So once we do all of that, we're going to end up with the relations that day x day u is equal to day v day y divided by the Jacobian. Remember that entire denominator was called the Jacobian. And also day y day u is equal to minus day v day x divided by the Jacobian. Similarly, when we divide it by delta v, then we get the relations that day x day v is equal to minus day u day y. Okay, this is a u in the denominator. Divided by the Jacobian. And finally, day y day v is equal to du dx divided by j. So going back to our original example that we had u is equal to e to the power x cos y, and v is equal to e to the power minus x sine y. So how do we go about finding dx du? Well, we'd need to find the Jacobian first, and the Jacobian, as you would recall from earlier, it's given by the determinant of du dx, dv dx, du dy, and dv dy. So I'll just write this again. Jacobian is equal to the determinant of du dx, dv dx, du dy, and dv dy. So substituting all of these things in, du dx, so u with respect to x, that's just going to be e to the power x cos y, because cos of y would just be a constant. So this is going to be e to the power x cos y. Then dv dx, again, sine of y is going to be held constant, so it's going to be e to the power minus x, and the derivative of the inside function is going to be minus 1, so we have to bring a minus to the front. So it's going to be minus e to the power minus x sine y. And then du dy, this is going to be just a derivative of cos y, so that's going to be minus e to the power x sine y. And then lastly, dv dy, so the derivative of sine is cos, so we're left with e to the power minus x cos of y. So the next step is to compute the actual determinant, and as you would know, we get the determinant by saying 1 times 4 minus 2 times 3, if this is 1, 2, 3, 4. So it would be e to the power x cos y multiplied by e to the power minus x cos y okay, minus, I'll write it in the next line, e to the power minus x sine y, this element, multiplied by the final element here, which is minus e to the power x sine y. So when we do that, we see that e to the power x multiplied by e to the minus x minus x is 0. So you have e to the power 0. Anything to the power 0 is 1. So we're just left with cos times cos, which is cos squared y. minus, same thing, e to the power minus x, e to the power minus x. All this gives us is 1. Sorry, I forgot this minus here in front, so there should be a minus here as well. So it's that minus there. So the minus times the minus gives us a plus, and again this gives us 1, e to the power minus x times e to the power x. So we're left with sine squared y. And this we know is equal to cos of 2y. Double angles. So how do we go about now finding the inverse, the derivatives of the inverse functions? Okay, as written earlier, dx du is equal to dv dy divided by the Jacobian. This is just simply e to the power minus x cos y divided by cos of 2y. This dv dy is something we had determined earlier on. Dv dy. So the rest of the differentials can be calculated in the same way, with dx dv equal to minus du dy divided by the Jacobian. Du dy determined earlier was e to the power x sine y. And this is divided by cos of 2y. The last two is dy du, and the formula for that is dv dy divided by the Jacobian, which is e to the power minus x sine y divided by cos of 2y, and finally dy dv is equal to du dx. Sorry, there should have been a minus here. Okay, I've put it in now. Lastly, dy dv is equal to du dx. Also, there should have been the minus sign there as well. Okay, so anyway, dy dv is du dx divided by the Jacobian, and that's equal to e to the power x cos y divided by cos of 2y. So perhaps it's interesting to get a perspective on how these relations were determined. So there was quite a bit of mathematical manipulation involved. Not to get hung up on all of the details, but it does matter in the end. So just a brief overview of what we had actually done. This was kind of a long one. We had two functions, u and v, as a function of x and y, and we want to determine the inverse derivatives. Instead of du dx, we want to determine dx du. So the first thing that we did was to write our function differentials, as we have been doing for the last few videos. Once we have done that, we multiplied these function differentials, equations 1 and 2, by dv dy and du dy. So we also needed to multiply this by du dy and dv dy, depending on what we wanted to make the subject of the formula, as we saw later on. So once we do that, we end up with equations 3 and 4. We then subtracted equations 3 and 4, and what we were left with was some of the terms cancelling out, and we left with day x day u equal to day v day y and everything else. And we saw that when we made the function, we made delta y the subject of the formula, we had a common denominator. And that common denominator we called the Jacobian. And we saw that this Jacobian was actually the determinant of day u day x, day v day x, day u day y, and day v day y. So in a matter of perspective, the Jacobian is kind of like a transformation quantity that transforms one partial derivative into kind of its inverse. We can think of it like that, but it's not actually that, right? But it is an important quantity to determine, and it also plays quite a significant role in other aspects of multivariable calculus, which we will see later on. So anyway, once we divide delta x, delta y by delta u and delta v, and set all the limits to 0, etc., we end up with these 4 very important relations, which is actually the mechanism by which we determine the inverses. For example, delta x, delta u is equal to, day x, day u, which is what we had wanted all along, is simply equal to day v, day y, which is something we can easily determine, divided by the Jacobian. And the rest of the inverse functions were determined similarly using the Jacobian and some variant of the partial derivative. And then we applied all of this into a example using our original example and determining the function derivatives or the inverse function or the inverse derivatives like that. So this was a bit of a long one, but nevertheless, the combination of the derivation and the example is important. And I think that getting this perspective of the Jacobian and how it's used to find the inverse is quite important. So thank you for watching.